And all the way from basically the fundamental physics, the fundamental chemistry, the fundamental material properties, all the way out into working devices. So the entire spectrum of that. So being from the basic theoretical point of view, the synthesis of these materials, spectroscopy to understand how the materials work, and then implementations into devices for specific applications. And these can range anywhere from using them as LEDs and solar cells, then to also just looking at the single photon properties. When we're looking at the materials, obviously, because it's about photophysics and light emission, we're obviously always concerned about how these materials interact with light. And so the main use of these are going to be in optoelectronic devices. I think that in the future there will be a lot more developments. I mean, as companies move then to implement new materials, as we try and, especially for example, in solar cell development, as we try and bring in different materials there to enhance the silicon capabilities, which are more or less maxed out. So, as an example, the perovskites and the tandem cells. I think there's a lot more to be coming there. I mean, especially with perovskites, the need for enhanced stability and enhanced durability is obviously great. And then in terms of light emission, quantum dot displays are still in its infancy. I mean, there are televisions that use quantum dots, but those are also mainly just used as phosphors, so they absorb light from the back LED and then re-emit it, instead of just being actually electrically contacted, so that the electrons. Those fields are massively impressive with what they can do, but there's still so much potential there to enhance and improve, reduce the energy consumption, reduce the cost of production, and then especially also decrease the actual waste at the end, possibly enhancing the capabilities of us to recycle the devices at the end, to be able to reuse these materials and not just have to dump them onto a wasteful somewhere.